how this is going to work or anything like that. But I have my stock Apache Hadoop slides that I've basically just put up. I don't know how we can do this, but so here. So forget about the. Forget about the agenda. I don't think we'll have time to go through all that. This is 2 hours, presentation. So just a little bit about me. I was one of the founding team members at Yahoo when I joined in 2005. The reason I joined there is basically that Yahoo had acquired a company called Inktomi, and then another company called Overture, which was sort of the AdWords model, right? And merging those two together, it became Yahoo Search. Now, Inktomi itself was like a 6-year-old startup, and Inktomi was, I think, the second search engine or second or third search engine. And they had developed all these search engine technologies, the back-end technologies at least, completely in isolation from each other, right? So indexing, crawling, all these different things were all developed independently, and so even if they had huge infrastructure, thousands of machines doing this search engine index building, they could not do this very efficiently. And also there were limits on scaling. I mean, we basically talk about big data nowadays. Right? Back in 2005, the web was probably hundreds of billions of documents, not at least tens of billions of documents. Now, Google recently published that now it's almost 1 trillion documents out there on the web. Getting all those crawled and indexing them so as to generate a search index so that a search engine could be built is a non-trivial problem. You need a lot of machines, a lot of computational storage power in order to do that. So the infrastructure that they had was not really utilized very well. So that's why they decided to replace all that infrastructure with something next generation. At the same time, Google published 2 papers. One was called GFS, Google File System, and the second one was the Google Map. So basically, based off of that design, we started, writing design documents back in 2005. In 2006, we came across, or actually end of 2005, we came across an open source project called Nudge, which was part of Apache Lucene, which was sort of an open source search engine. Doug Cutting was the person who actually started Apache Lucene and Apache Nudge, which was the content system for Apache Lucene. And then he also independently came across these 2 papers and just did a preliminary implementation of the file system, a GFS clone, as well as Google Map. And we noticed that by the end of December 2005. We hired Doug Cutting as a contractor and basically convinced him to split off this part, which is the GFS and the GFS clone and the MapReduce clone, into a separate Apache project called Hadoop so that Yahoo could contribute. Right? And then Yahoo built a team, almost 20-25 engineers working on Apache Hadoop. We acquired our first cluster, I believe, when I was in Yahoo. I believe in March of 2006, around 600 machines, and took Hadoop from a 20-node sort of prototype to what it is running today, which is about 45,000 machines in Yahoo actually running. Okay. So it's all of Yahoo's business actually goes through that. So I have some slides to show you all. So recently, last year, I left Yahoo and spent a few months in LinkedIn and then joined Greenplum because they were working on their own strategy. So if you see this, if you have gone to Yahoo front page, you basically see www.yahoo.com, you basically see these a bunch of, hey DJ. DJ, by the way, is a big player in the big data and Hadoop space. So I'm glad you could come. Right. So if you go to www.yahoo.com, you basically see this a small frame in there that basically says these are the stories that, current stories that you might be interested in, right? So this this is called the Today module. The Today module goes through all the stories, all the videos, all the pictures that are out there in Yahoo's content database, and based on who logs in, based on their previous behavior on the Yahoo website, right? They generate, okay, this might be interesting for one of you, right? I mean, for the person who logged in, right? For example, people logging in from India will typically get shown cricket stories, not football or other American sports, right? So that's how does Yahoo decide that? It's basically based on your past history, right? First of all, and then if you are logged in for the first time, then just it starts learning from your behavior at yahoo.com and decides on these today module. So this is done on top of Hadoop. Every 15 minutes, something like 3 million such today modules are generated. So the entire Yahoo user population, about 600 million people that log in maybe every month or so, they are sort of divided into these 3 million categories, and depending on which category you fall into, that's the today model that is shown. This is one of the workflows or actually data flow diagram for the Yahoo advertising pipelines. All the data collection, all the data ETL that happens, all the aggregations, all the model building that happens, this is all the entire, I mean, there's like 600 or 700 different steps that you have to carry out on this massive amount of data, multiple terabytes of data. So this is basically the total workflow that is implemented on top of Hadoop. Okay? So who uses Hadoop? Well, back when we started in 2007, it was Yahoo and a few adventurous souls. But as you see, 2010 and 2011, I could not fit it in there because it's too many logos, right? So 2010, you can see a lot of familiar names. 2009, 2010, a lot of familiar names. And now it is actually very difficult to find a vendor or a company that does not have some sort of Hadoop strategy. So you basically go to Oracle, Teradata, Greenplum obviously, and all the database vendors. They have some sort of Hadoop strategy, either connecting to Hadoop or, as in Greenplum's case, it's our own distribution of Apache Hadoop that works very well with the implementation. So it's gotten really popular. Axel recently, and this whole thing combined with the whole notion of big data is basically generating a lot of interest. So that brings me to my next topic, which is why Hadoop and why now. Okay. This picture that I have taken is actually from a 2007 proposal that somebody made from the University of NSF to fund some research. Right? The 2007 data sets, even at that time, you basically find a few petabyte size data set. I mean, 1000 terabyte is a petabyte. Right? People typically don't think about peta, and now people are talking about exabytes, so like 1000 petabytes and stuff. So how do we get all this data analyzed in a timely manner in order to generate business value? That's basically what people are talking about. Right? Twitter itself, if you go to, if you subscribe to their what they call as the firehose, which is all the tweets anyone makes, right? It's about 12 terabytes of tweets are generated in one day. 12 terabytes, right? And if you are basically going to be analyzing all those tweets for maybe sentiment analysis or, what are people talking about, what are the trending topics, or maybe that is not very interesting to you, but if you are, for example, Apple, you announce iPhone 4S, right, after this big fanfare, and then after that, now you start monitoring what people are saying about it. This is basically marketing campaigns analysis. All these things happen based off of all these social data. Anytime you make a connection, maybe on LinkedIn or Facebook or Twitter, you follow somebody, you're essentially adding on to this corpus. So this data is literally exploding, right? And there was a study that was done, sort of taking the sample of various data sets that are out there in the company. It's something like, I forget the numbers, but by 2018 there will be something like 35 zettabytes. That's 1000 hexabytes. I don't even know what comes after zettabytes, but it will be there soon, right? So that's basically where it is going, and 80% of that data is unstructured. does not fit very well into the traditional relational database management system. It's not like fixed set of columns or fixed number of rows or fixed types or whatever. This is basically all the junk that people post on Facebook or Twitter. All that thing is plain text, has literally no structure on it. How do we extract information from there? How do you actually create business value out of that? That is the biggest problem that we are facing right now in this big data era. Fortunately, what is happening is that the storage cost is getting lower and lower. Right? Back in probably, I start this graph in the 70s or something like that. Back in the 70s, it used to cost like literally a fortune to buy a gigabyte of disk. Right? My first PC, if I remember, back in 95, had a whopping 212 megabytes of hard disk. Today, my memory is more than that. My RAM is more than that, right? On this laptop. That I paid like 2,000 plus for that PC. So now the cost of storage has come down to a few cents per gigabyte. You go to Fry's, you get a 2 terabyte hard disk or 1 terabyte, 2 terabyte hard disk almost for 60, 70 bucks. Right? So you're literally getting down to 3 cents a gigabyte. So the storage cost is going down. That is one good. The second trend that we are seeing is that the storage densities have gone up tremendously. In the small 2.5 inch hard disk, now you can pack multiple terabytes in there, at least 1.5 terabytes in that space. Right? But the amount of time that it takes to access data out of it, which is determined by the storage bandwidth, that hasn't been increasing that much. Right? Back in the days when we had this 212 megabyte drive, I could probably scan the entire drive within 30 minutes. Read all the bytes on that drive within 30 minutes on my PC. Today, if I basically start reading a 3 terabyte secret drive, it will take me a couple of days at least to read everything out of it. Right? So how do you then, when you have such a lot of information, how do we access that very quickly? Right? So the way you do this is, if you have a huge data set, let's say a terabyte of data set, you store it, you partition it and store it across a lot of different disks and then read all of them in batch. That's basically how you do it. And that's what gave rise to the whole notion of distributed computing and parallel computing. Because you need to get to that data as fast as possible. So that's where Hadoop actually comes in. Alright, so a few examples where Hadoop has already been used. I mean, I sort of hand-waved and say, today module is generated using how, right? So one of the things that you might have noticed, and this is from Yahoo search, but Google has a similar feature, the autocomplete, Bing has similar features, that you start typing a search term, and by the way, a lot of my examples are from online space because that's where Hadoop really originated and shown. And now it is getting into retail, manufacturing, all those big data sets. That's where it is going. But it came out of that internet online space. So you start typing these search terms, and magically Google or Yahoo or Bing, they actually tell you what to look for. I mean, they just autocomplete that term, right? I mean, whatever. I mean, people have sort of made it into a game that you start typing and then what does Google suggest, right? So Google search suggest is basically like that. So this is an example. I start searching for Hadoop, and Yahoo search shows me a bunch of other things that I might want to narrow my search, Hadoop streaming, Hadoop focus, or something like that, right? Okay. So the insight is very simple. How do you build this thing? Well, of course, you cannot go across all the documents that you have seen, or documents as in all HTML pages, after you start typing the search term, Google or anywhere. So what they do is build an index upfront, which basically says, if this is the word that people are searching for, then these are the words that you should suggest them. So that's basically sort of a lookup table, if you call an index that you look for, right? And they built this completely offline. So this insight is really simple. I mean, I made it like the actual algorithms are much more complex than that, but in order to understand how this is built, it's fairly simple. You have these trillions of or billions of pages that you have crawled from the web, right? You have the HTML sources all out there, right? If the search terms are related, right, then the insight is that a lot of these pages will have those two terms
occurring together, right? So when you start searching for president, right, then the next word in that will probably be Obama, maybe past presidents, Bush, Clinton, all those things, right? How does Google or Yahoo even know that president is related with Obama? Well, because President Obama, these two terms occur in a lot of documents out there on the web. That's pretty much it, right? But the problem now that happens is that now we have let's say 1 billion pages. Each page is compressed about 10 kilobytes. So now we are talking about analyzing 10 terabytes of data, right? How do we analyze this 10 terabytes of data, just the text data, and build this index, right? Forget about the pseudo code here, but really what you have to do is just extract all the word pairs that are occurring. I mean, I'm just giving an example of two words. So extract all the word pairs that occur anywhere on the page and find out which are the most frequently occurring word pairs along with a particular word. So if the first word is president, then what are the most frequently occurring top 3 or top 5 terms that occur after president? Probably it's going to be Obama or Clinton or something like that, right? Okay, so that's basically that. The second example is basically when you log into LinkedIn, you'll basically see there are this on the right hand side, on the top right hand side, you will see these are the people that you might know. Okay. Now, again, the same thing. You can't go through all the 130 million LinkedIn users to see after you log in as to who you know. You build an index offline. Now, how is this index built offline? Well, again, the algorithms might be complicated, but idea is simple, right? So if I know you, and a lot of people that I know also know you, right? A lot of people that I know you, but I don't know you yet, right? Then since I can basically connect to you from various other people, there is a more likelihood that I actually might be knowing you already, right? So that's essentially what it is. And if you again look at the pseudocode here, you basically have to go through each and every user pair that you have, and you find how many paths there are between this user and that user, okay? And then maximize on the number of paths so that you basically say that, okay, these are the top 3 people that you might know, because a lot of people that you know already know that person, right? So that's basically. But if you look at this for loop, I mean, probably some of you cannot see it. The inner part is if you have 100 million users, and let's say each one of them has another 100 connections, and then each one of them has other 100 connections, this thing is going to be executed a trillion times, right? So if you basically just look at if you look at the performance of this, obviously all this data cannot be stored in memory. It's several terabytes of data, so it is going to be on disk, and most of these data accesses are going to be random accesses, and disks are notoriously bad for random accesses because there is this mechanical platter that is moving, right? There is this mechanical component, the mechanical arm that has to keep on moving, and so 10 milliseconds to 5 milliseconds is what actually each of these seeks takes on the disk, right? And that is going to, if you basically do all this calculation, then in order to compute these people who may know that index, it's going to take 100 days on if the data is stored in a database on a single machine, right? Obviously, in those 100 days, you probably have already added that person in your network, right? And then what happens if you log in and one of your connections shows up as, people you may know who you haven't connected? Well, that's a bad user experience, right? So this is one of the things that LinkedIn actually uses Hadoop for in order to generate these people you may know. And after the people you may know success, now there is jobs you may like, groups you may know. So Facebook uses Hadoop in order to generate these lists. Facebook also uses Hadoop to generate the application analytics, the web page analytics. Lots of stuff is actually being done in the online space, at least on top of it. Okay. Any questions so far? Okay. Cool. So, all right. So let's look at what made Hadoop possible and what are the core components of Hadoop. Well, the core components of Hadoop essentially are what is called the programming paradigm for Hadoop. I mean, when you write an application using Hadoop, most likely you're writing a MapReduce application, right? So what does the MapReduce application look like? Well, the map and reduce, this is not something really new. The map and reduce functions or the sort of the primitives have been part of programming languages like functional programming languages for more than 30 years, 40 years now, right? What made the popularity of MapReduce possible is that in 2004, Google published a paper saying that all their machine learning and all their search indexing algorithms are actually implemented using this programming paradigm, right? And then people sort of started, oh, I have this algorithm, why am I doing this complicated algorithm when I can actually implement it in MapReduce, and instead of doing it on one machine, I can execute it on thousands of machines, right? So just throw big hardware at it so that you can quickly iterate on building your applications rather than just focusing on one application and spending your entire lifetime trying to optimize it, right? That was essentially what came up. So what does this map and reduce look like? Well, very simple primitives. You take a huge list of data items and you apply the map computation to it, which basically means take each element in this list, right, and apply some computation on it. The simplest form, you basically have a list of integers, you are squaring each one of them. That's basically what a map is, right? Now, if you look at the map, if you are computing a square of 4, you don't need to look at 5 or 3 or anything like that, right? So this is what we call as the trivially parallelizable application, right? Trivially parallelizable. You get million entries, and if you have million machines, it will all go with, you can fire all million computations simultaneously. No communication is needed, right? The second part, though, is slightly complicated in the sense that the reduced computation takes an entire list and applies some sort of an aggregate function on the entire list, right? So if you are given a list of numbers and adding them, all of them up, you basically need to read each one of them, right? Yeah. So if you have done any parallel programming or any of, if you have thought about how we can parallelize this, well, the reduce is the one that is actually going to create problems for you, because that has to be executed on a single machine. Right? So what Google did is they basically introduce something between map and reduce, what they call as the shuffle. Okay, what they do is the map computations are distributed all over the machines, the entire cluster, and then the output of that map computation is somehow grouped in order to produce multiple lists. When you have multiple lists, then each of these lists can be processed completely independently in the reduce phase. That basically was their secret sauce that they added between map and reduce. So this is what is called as the map reduce programming frame. All right. So let's come back to the search assist example. Now this is what it was trying to do is it was going over all the web pages that are out there in your crawler corpus, right? And was trying to determine which was the most commonly occurring term along with one particular term, right? So the first step in that is once you have all these page text, the HTML, right? Take that and generate all these word pairs that you find in there. Okay, so now this is, as you see, in order to find one web page's word pairs is completely unrelated to finding another web page's pairs, right? So this can be done completely independently, and therefore this can be done in a map computation. Take a URL, you fetch its text, you take out all the HTML junk that you have, the tags, etc. You take the text out of that. For every text line that you find, for every word, find its next word, that generates your next pair. Find the next word, that generates your pair. So if you go to, let's say, http apache hadoop.org, this is basically the Apache Hadoop website that has a bunch of HTML, you will find that you will get something like this, a bunch of word pairs. Right? Now, the shuffle stage that I talked about, which is going to actually produce multiple independent lists, what that is going to do is it is going to take the first word from each of these word pairs and say, you know what, this is the word, and what are all the words that come after this, and these are all part of word pairs. They are all combined together and sent to one reduced computation. So after this, the shuffle kicks in, and then what it will get is whichever page in the web that the word Hadoop occurred in, the next words from all those pages are going to get sent to one particular machine along with the word Hadoop. So you'll basically find in the reduce side, you will basically find a word and a list of words that follow from the web corpus. Right? And now all that you are doing is just counting how many times it occurs. That's pretty much it. So that's your reduce computation. So after this, what you will get is along with Hadoop, the next word that occurs is Apache 7 times in this entire web corpus. So once we have this, now it is very easy to sort this according to the word that you have. Take just the top 3 and throw the rest of them out. And so now, and put that in an index so that when next time somebody starts typing Hadoop, we will show that, okay, these are the top 3 candidates for your search assistant, right? Make sense? All right. The problem that happens, obviously, I mean, this is very simple to describe. When you actually are implementing it, there are several issues, right? So obviously, the problems that occur are mainly with the scale of the data, right? You are not talking about a few gigabytes of data, which now actually can fit in my memory, and I don't need to implement MapReduce if it's only a few gigabytes of data. Depends, of course, how quickly you want it, etc. But how do you take this terabytes of data? How do you distribute across the number of machines that you have, and how do you push the computations to work on this data? So that's one thing, right? The second thing, grouping, we have already seen. Hadoop or Google MapReduce actually provides you with this grouping functionality built in, so you don't have to do anything like that, right? But now, when you are implementing this on top of a large cluster that you just probably bought from Fry's, a bunch of machines, you just hook them together on the network. Well, of course, these machines, even if they are touted to be to have a sort of a mean time between failure of the lifetime of 3 years or 5 years, some of them break. Right now, if you are running an application that runs for one full day, right, on this 1,000-node cluster, and if one machine suddenly fails, okay, do you restart the application from the beginning? If you do that, you have just wasted 1,000 machine days of computations, right? So you need a resilient implementation of the resilient middleware in the cluster that can keep the application going even if some of the machines, some of the disks fail, right? So that is the second. All right, so that's where Hadoop comes in. As I said, in January 2006, this was a sub-project of Apache Lucene, right? Now, today, the version the stable version that is available after 6 years is Hadoop 1.0. Right? Just recently came out 1.0. Now, the next version, don't get confused. The next version is going to be 0.23. Hopefully, it will turn out to be either 2.0 or 3.0 or something like that. But right now, it's called 0.23. Major contributors: Yahoo, and now it's a spin-off. Hortonworks, Cloudera, Facebook. These are the guys who have been contributing it for a long time now. Right? So, what it is, at its core, it's basically a reliable distributed file system, because when you are storing petabytes of data, you cannot store it in a single box. You have to have multiple boxes connected over the network, and now you need this to be reliable and keep on functioning even if some nodes, some disks go down. Right? That's one thing. So the distributed file system is very important. The second one, the core part, is the MapReduce programming framework. Now, once that became sort of popular and useful, people kept on adding additional functionality to it. So you will find funny names like Hive, Big, all those Hive, Big, HBase, cascading, a bunch of things, right? So there is a large ecosystem now created around Apache. These are basically a lot of programming frameworks. A SQL-like interface is on top of Apache Hadoop is called Hive. There is a higher-level language that essentially translates into Apache MapReduce, that's called Pig. There is a NoSQL key value store. By the way, have you heard of this term NoSQL, right? Everybody is saying NoSQL right now, but anyway, whatever that means. But NoSQL key value store called HBase. There are lots of projects out there. Okay. All right. So what are the two main problems that Hadoop tries to solve? First one is the bandwidth to data problem. Right? In your traditional storage architectures, what you have is a compute cluster right? And a storage cluster, SAN, NAS, whatever. So these are the two separate boxes, right? Or boxes or collection of boxes. Now the problem is that when you are transferring the multi-terabyte data from your storage cluster to your compute cluster, well, the pipe between these two clusters, that's going to be your limiting factor, right? I have some numbers here basically say that even if you have the fastest network data center networking in the world, this is the problem that it is going to create, that it's going to be bound by that network pipe. You don't have enough bandwidth to feed all the CPUs that are running, right? So the way Hadoop tries to solve this problem is that instead of keeping the data, the storage cluster and the compute cluster separate, essentially overlaps. Right? We used to have a saying in Yahoo that when we buy a machine, we are buying it for storage, we get CPUs for free. CPUs and memories essentially comes for free. So you have a single box in which there are 6 or 12 2 terabyte drives, 4 quad-core CPUs, 64 gigs of RAM, etc. So now you are using it both as your compute box and your storage box, right? So your compute cluster and the storage cluster is overlap. But now what happens is that the data is obviously distributed across all these machines, all thousands of nodes, right? Now you need to know where the data is so that you can schedule your computations closer to where that data is, preferably on the same box on which that data is, right? So Hadoop file system, essentially, a lot of file systems out there, distributed file system, you might have heard names like Lustre, Isilon, all these cluster file system. They try to hide this information. They basically, you open a file, they don't tell you which box, which disk that file is located, right? That's not going to work in our case. In our case, we need to expose that information so that the MapReduce framework then actually puts the computation to where the data is, right? Rather than moving the data to the computation. Because computation is expressed as maybe a small Perl script, or a Java program or something like that, which is maybe a few kilobytes, right? But then your data that you are operating on terabytes, would you rather move terabytes to kilobytes or kilobytes to terabytes? That's basically the choice that you have, right? All right. The second thing is handling this failure reliably, node failure, right? Let's say you get 2 machines from Fry's or from Dell.com or whatever, right? They will tell you that the average, the MTBF, average mean time between failures for these machines is 3 years, right? So you expect that you bought the machines, you plug them in, now 3 years they are going to run perfectly okay, right? Well, that's the mean time between failure. If one machine fails immediately and the second machine fails 6 years after you plug it in, the mean time between failure is still 3 years, right? 6 plus 0 divided by 2. So they're talking about mean time between failure. Now, this problem gets exacerbated when you have thousands of these machines together. Right? And this is not some theoretical calculation. We have actually seen this happening in Yahoo. In Yahoo, 1% of our cluster machines used to go down every month. And the problem typically, I've seen all sorts of problems in operating the clusters at Yahoo. Somebody coming in and yanking the wrong cable from a wrong box, right? The machine is suddenly powered off. What do you do about that? But the main culprit in most of these machine failures is the disk, because that's the only moving part that is out there, right? So disks, I've seen disk failures range from, the disk suddenly getting read-only, disk running out of space. Those are sort of the programming problems. But I've seen all sorts of errors, silent errors, all sorts of things happen, right? So if just one disk or one node fails, you don't want your entire cluster to come to a stop. It should still keep on going. Obviously, nobody expects that 10% of your machines go down. You still have to keep on functioning like nothing happened. Well, at least fail graceful is basically what we are saying, right? Don't say the entire cluster is offline because 10% of your nodes are on. So that's basically what Hadoop is trying to do. Right? Okay. So what are Hadoop goals? First of all, it needs to be scalable. It needs to handle petabytes of data, because that's essentially the space that we are in, right? We have seen how expensive it is for the traditional database companies to store petabytes of data, even if it is possible. I think the biggest example biggest RDBMS that I have seen, I think, is implemented in Walmart using Teradata and about 500 terabytes. That's about what it is, right? But several terabytes nowadays RDBMSs can go there, but petabytes is still unseen by RDBMS, and just the whole overhead of indexing, all these things are just not possible with the RDBMS, right? So we need to be scalable. We need to scale to petabytes. We need to be reliable because we are flashing together all these commodity components and creating a single large resource out of it. And the third one is that we don't want to have backup batteries. I mean, if you have them, it's good, but we don't mandate that you buy this expensive hardware which never fails, has a redundant copy of everything, 2 CPUs, one just sitting idle to take over, or some memory banks that essentially are, we don't want that expensive hardware. We basically want an economical hardware, lash it together, build a single largest resource, and let the software handle all of the reliability, all of the fault codes. That's basically where it is. So I think that's pretty much what I can cover in this, and I'll take questions. We'll make this interactive. No. Yes.
I understand Greenplum source Hadoop. How are you guys making money?
Greenplum actually, so a lot of Hadoop is an Apache open source project. You can just you don't need to go to Greenplum, Cloudera, or Hortonworks in order to use it. You can just download it off of there and just start using it on Hadoop, right? So the money is being made in support licensing cost for some proprietary components. I mean, Greenplum, for example, has a tie-up with another startup called Mapr. Mapr is an interesting file system in the sense that they essentially looked at Hadoop file systems for the last 2 years and basically identified the gaps in the Hadoop distributed file system that typically people come to expect in enterprise market, right? Which is like NFS access, snapshots, mirroring, the things that you traditionally expect out of enterprise file systems. So they built a proprietary file system. So everything else is Apache for them. There is no HDFS, there is Mapr there, right? So that's the proprietary one. So that's we are reselling that branded as Greenplum MR. So we are getting license revenue for that. But for the open source, we also sell the open source version, which is sort of the packaging of different open source components. But that's only a support revenue for that. Support and training.
Similar to Red Hat.
It's very similar to Red Hat, right? For the open source, it is very similar to Red Hat open source version, which is what we call as the community edition or GPHD. The enterprise edition is a licensing model based on the Mapr file system.
So you mentioned that I can understand all the search engines and all that, but you mentioned this can be implemented in other, not just online.
Right. Yeah.
So in that case, can you give some examples? What's the total expenses for that company?
Sure, absolutely.
Let's pick some mid-level manufacturing company.
Sure, exactly. I will give an example in, let's say, banking. Right? Banking is close enough. Their structured data, everything is there. Right? So we recently implemented a solution along with Greenplum database and Hadoop working together on a modeling problem. Right? So what has emerged is basically that earlier what people used to do is take a small sample out of the data that they have and build like some mathematical models, statistical models on top of this, right? Banking example, I could basically say, how likely is this customer to close the account, right, with us and move on to our competitor, or how likely is this loan applicant to default on the loan, right? So what people used to do is basically just take a few representative samples, like maybe if you have 1 million customers, just take about 1,000, build a mathematical statistical model using that, and now apply that to the million customers that you have and determine how likely is each of them. Sure, that's basically it. So now what is becoming possible is because of this huge compute power that you have at your and storage that you have at your disposal, you basically build a model on all your customers' data. Right? Earlier, you were basically considering only their income, their location, probably their past credit history or whatever. Now you can integrate social data. Now you can basically say, oh, this guy is connected to some, go-gooders from Facebook, so probably is more likely to default. And that data now you can get from Facebook or from Twitter, LinkedIn, all those things. So more data is getting absorbed, more extensive models are being built on the same data. And so that's how Hadoop actually helps in that space. Right? Manufacturing itself, well, I don't have a direct experience in that, but some folks that I have talked to basically say they actually have a lot of sensors embedded in the manufacturing processes. They are generating tons of data, right? Now, we would like to know, based on those sensor data, we would like to predict, and this is most of the examples in there are sort of predictive modeling. Based on the past history, can we actually predict what is going to happen in the short term? Those are the kinds of problems, very computationally intensive, very storage intensive because of the large sensor data that is being generated. So that's basically what people are using it for. EMC last year actually conducted something called a Data Science Summit, which is a lot of these people from various disciplines that do sort of this data science. And data science is sort of emerging new technical discipline which combines statistics, Hadoop programming, or databases, Hadoop programming, all these things. So people basically, I mean, LinkedIn, Facebook, all these were sort of the pioneering companies that started a dedicated data science team. So that has now spread to a lot of different disciplines or different areas, verticals. So one of the people who were called in there was from the healthcare industry, and in fact from government. The project that they were doing was for actually government to predict the contagion, how a disease spreads, right? So they were looking at all the CDC, the disease center, the Center for Disease Control data that they have available, right? They essentially said that, after a flu outbreak, maybe about 3 weeks after that, CDC comes to know about it. Let us try to predict it. So Google flu trends is actually one of the things. When you have this flu contagion, right, happening through outbreaks, people start searching for flu symptoms. I mean, do I have flu? That kind of thing, right? I'm feeling warm. My head is hurting. All those kinds of things, and you will basically see that the place where this flu outbreak begins. If you have the geographic location for the queries on that data, you'll basically see a spike in those search terms. That's what Google Flu Trends is all about. These guys actually took it to the next level, which is, if people are searching for it, maybe they are even tweeting about it, or they are posting status updates on Facebook saying that, oh, I don't feel good or something like that. These guys could actually predict an outbreak exactly at the time even before it happened, because when this guy now goes to changes his location on Twitter or changes his location on Facebook, they can basically say, oh, this guy had flu just yesterday. Now he's moving, so probably he's going to spread flu there. So a lot of these very nice applications getting there. Really.
So when you talked about the fire hosing of data with Twitter and things like that, right? For a common business that is practically trying to analyze their customer behavior and want to feed in Twitter data or any other such social data, are they actually physically transferring that data, or the queries are being executed remotely?
No, they are actually transferring that data. I mean, nobody that I know of, nobody that I know of actually subscribes to the entire Twitter firehose. So what you can do is actually just search for certain keywords in tweets and just filter them out at source itself, and get that small amount of data.
But that filtration happens
That filtration happens on the
within
API
Twitter's
side. Yes,
infrastructure.
yes, that's right. So they actually have, in fact, outsourced this. The tweet distribution thing, they have outsourced it to two companies. I forget. One of them is in Colorado. One of them is here. Yeah, GNIP. Yeah, GNIP is in Colorado. So GNIP is the one that actually provides you the Twitter firehose. A sample, really.
Oh, the sample.
It's mostly a sample, and you can actually do a filtering on GNIP side and send it there.
So just through the API, you can make calls.
Correct. Exactly. Yeah.
So for an early stage, startup company of angel funding,
Right.
what is the incentive to use Hadoop? I have limited money and I know it costs a lot of money to rent a lot of machines. What do I do?
So if you basically see the way Amazon Web Services are going with, that is actually okay. Let me back it up a little bit. Right? Back in 2007, 2008, some people, now they are part of Cloudera. They basically said, you know what, this Amazon EC2 and S3, Amazon Web Services, make a lot of sense because now you can just spin up a cluster of instances in 10 minutes, right? And you basically say, okay, I need 100 instances clustered, running quickly. And now you can they wrote scripts and they basically made it easy to deploy Hadoop on demand onto those 1,000 machines or hundreds cluster instances in AWS. So Amazon took that idea even further by offering a service called EMR, Elastic MapReduce, where you don't have to actually grab the instances and set up Hadoop yourself. You basically just say, this is my Hadoop job, go run it, right? And they will basically scale according to the amount of data, a lot of other factors, and will send you a bill at the end, right? It's 10 cents a CPU hour or 15 cents a CPU hour or something like that. That's pretty much it. So you don't actually need to maintain your cluster forever in AWS. You can basically say, whenever, if your data is already stored in S3, whenever you want to run, you can basically just, from a web UI, you can just submit a job and get it done, right? So that's actually getting out to be a pretty attractive options for startups.
You made an interesting comment. If your data is already in S3,
Yes.
Otherwise,
You have to basically upload it. That's basically the thing. That's where I think.
That's where they squeeze your money.
Exactly. That's 10 cents a gigabyte upload.
Yes.
So yes, that's where they squeeze your money. So, but the rest of the infrastructure, like they also have a serving infrastructure now. They have the edge network, edge cache, and all those things, Akamai things, right? So, if your rest of the serving infrastructure is also there, you are probably collecting the user data or whatever data that you are interested in S3 anyway. So if you have that, then your backend processing can also execute in AWS.
So in your opinion, or in your experience, storing massive amounts of data in S3, or from what I have seen, it hasn't looked economical for me.
Well,
Do you feel otherwise? Very large amounts of data. When you're
sure,
talking
obviously.
50, 60 terabytes and above,
Correct.
right?
Nobody uses it for that much of data. That is clear. I mean, other than Netflix. Netflix is
That's
like the
also
crown
for edge
customer.
caching and storage, just for streaming.
Well, all their data analytics is happening in AWS as well. All the analytics, I mean, if you see the movie recommendations, those are all there. Those are all happening from AWS. So,
How disruptive is this traditional database?
well, just based on the database industry's response, yes, it is. It is definitely disruptive. Right?
Microsoft.
Exactly. So Oracle recently announced a partnership with Cloudera, one of the Hadoop solution providers, Hadoop distribution providers, that their Exalogic analytics appliance is going to be running Cloudera. Microsoft has two strategies. One is going with Azure, their hosted cloud service, plus making simpler for Windows Server to deploy and run Hadoop. So that's the two-pronged strategy. I mean, that's what they say. Any database vendor that you see, they have a Hadoop strategy. Teradata has connectors, HP Vertica has connectors, Greenplum obviously has connectors that they include with the distribution. IBM has what they have their own distribution called Big Insights, and a lot of their acquisitions that they made, they are basically connecting with Hadoop as well. Netezza has connectors to it. So everyone has Hadoop connectors today.
Also, just follow-up question. See, we are addressing a search kind of analytics. What about transactions?
Right. So the transactions, if the transaction, so first thing to note is that when you have the, I mean, this came out of something called the CAP theorem. Eric Brewer was, he proposed that CAP theorem. So what it says is that in a large distributed data system, right, you basically have three properties that you desire, right? Consistency, which basically means the transactionality. That's what atomicity means in the ACID, right? Availability, which is, your system should be available in spite of failures of, different nodes, different networks, whatever. And the second one is partitioning, which basically means that when you are designing a distributed system, right, there are going to be components in there. If that fail, your distributed system is going to split into multiple partitions, right? So these three things that you have. So the CAP theorem states that you can have only two of them. I mean, it's like a rigorous scientific proof that you can have only two of them, right? So if you have transactions and if you have availability, then you have to be within the same data center, in fact within the same cluster, right? You cannot have one cluster in China and one cluster here and still have the same properties, right? So what Hadoop and all these NoSQL systems do is sort of take the AP approach and forget the C. So you don't get transactionality, you don't get consistency in, but then you have availability and you have large geographical scale. You can have partition, right? So what we are seeing today is that people are not junking their database systems, RDBMSs, and just going with Hadoop. Right? They are essentially putting Hadoop to take off or offload all the computationally intensive thing that they used to do earlier in the RDBMS. Now they are moving it there. Right?
So, but ultimately the delivery mechanism still is in the RDBMS systems for largely for now.
So
the BI delivery is still happening there. The
Yes.
computational happens on Hadoop and then transports to the
Exactly. So what people do is all the transaction. I mean, I'll give a LinkedIn example because LinkedIn I worked there for 6 months at least. But so all the results etc. that you see on when you log in, right? The real time stuff that is happening when you log in, that's actually coming out of Oracle, right? Now any changes that you make. Add a connection, right? For example, invite somebody to connect. Well, the transaction is entered into Oracle, right? So Oracle gets that. But then the copy of the transaction, that the fact that the event that the transaction happened is also streamed to a Hadoop cluster, and that's where it is all kept, right? So now what we have is a transactional system, Oracle. All the changes that happen in that database are streamed off to Hadoop as well. So now at any time you can essentially reconstruct that Oracle DB instance on the Hadoop cluster, right? So you're not taking daily snapshots or anything like that from Oracle, and just in order to do your analytics tasks, you can now actually just keep Oracle, leave Oracle alone, and do your analytics tasks on the latest available data.
We'll be wrapping up the powerconnect session in 2 minutes.
Can you talk a little bit about the people that are required, all the skill sets across the pipeline?
Sure. So that is getting to be a lot of trouble now, right? So this whole, there was a survey done by McKinsey that came out I think last year itself. So it's a rare survey in the sense that McKinsey typically charges like hundreds of dollars for its surveys. It's actually available for free, thousands, but now it's available for free, right? I don't know what prompted them to make it free, but anyway. So what they said is that over the next 3 or 4 years, they're going to need around 150,000 data scientists, right? People with statistics, people with just the data handling mindset, right? So that is getting to be a lot of problem. But then what people are doing is people are stepping up with training. EMC, for example, has a data science course, 5-day training that they offer. Cloudera and Hortonworks, both of them are actually offering Hadoop specific courses, again 5-day courses. databases. And I've seen a lot of, I mean, North Carolina State University has actually started offering Masters of Science in data science, data analytics. Right? So people are trying to address those gaps. But this is, if you have to develop on top of Hadoop, what I find is that just great systems level knowledge rather than specific knowledge about Hadoop or anything like that. Couple of months, 3 months, you can train your existing people in order to deal with Hadoop rather than trying to hire in this hot market. It's amazing. I mean, 30 to 40% premium over median salaries for the same amount of profession, the same amount of experience. It's getting crazy. It's getting crazy.
Do you feel that Java is very important for anybody who is working through Hadoop, or
if you want
are
to
the
develop
interfaces like big good enough?
Right. So I think one should not write MapReduce programs anymore, as in Java, right?
Meaning you use
basically use Hive, use Pig, right? If at all it cannot meet your needs for some reason, only then think about writing MapReduce programs in Java.
What's the differential in performance between
It should not be much. I mean, for most common queries, the Pig performance is actually between 10% of the MapReduce performance. But in
So we
order
have
to get that
completed the
MapReduce
powerconnect
performance,
session.
it's going to take a lot
So
of time.
please give a big applause to all the powerconnect session leaders. So now we will start the keynote session.
Thank you.
Sorry, I didn't mean
Hey, good. Happy New Year. Meeting for the first time at Greenplum Labs.
systems are using Infineon.
Infinite, yeah.